Hey everybody, we're back in chapter 4 again, and this time we're working with exponential functions as opposed to exponential equations. And our goal in this section, the first one, is to sketch a graph of an exponential growth function, and also to be able to sketch the graph of an exponential decay function. Alright, so you're going to need to know what an exponential function looks like, period. And then we'll learn how to determine whether it's exponential growth or exponential decay that we're actually trying to graph. Alright, and I'm going to show you those things in the following slides. Here's an example of what an exponential function looks like. Whenever we're talking about an exponential function, we're just talking about a function that can be written in the form f of x equals a to the x power. Alright, so it's a function where the variable, the input variable, is part of your exponent. And an example of an exponential function would be y equals 4 to the x power. And that's what we're getting ready to graph right now. Okay, so basically what I want you to learn from this is what does the shape of an exponential function's graph look like. And it doesn't have a special name like parabola for our quadratic functions. It's just a shape that you need to know, however. And we're going to determine what that shape is simply by using an xy table here to plot some points that would exist on the graph of y equals 4 to the x power. And I'm choosing to plug in 0, some positive exponents, and some negative exponents. Remember, the x represents an exponent right there. Alright, well, let's start with the positive values because these are the ones you know the best. If I plug in 2 for x, that's going to give me 4 squared, which is going to be 16. If I plug in 1, that's going to give me 4 to the first power, which is 4. If I plug in 0, well, you know that 4 to the 0 power is equal to 1. And then recall with negative exponents that you flip the base whenever you are evaluating a negative exponent. So 4 to the negative first power is 1 over 4 to the positive first power, which is 1/4. And 4 to the negative second power would be the same as 1 over 4 squared, which is equal to 1/16. Now here's a big thing that I need you to notice. None of these values, none of our y values there are negative, are they? If I have a positive base and I raise it to an integer power, well, it doesn't matter if it's integer or not, truly. If I raise a positive number to a power, I'm not going to get a negative value as a result. Alright, so we're not even going to be using this portion of the graph right here. Great. Now, we also want to plan ahead as far as what the scale is going to be on our y-axis. If we're trying to go basically from 0, which is what 1/16 is very close to, up to 16, you might consider going by 4s or 5s or something like that on your vertical axis. I'm going to go ahead and label my intervals real quick. And you can see I've chosen to go by 5s because every other interval is a 10, right? That's 5, that's 10, and so forth. And let me go ahead and plot those 5 points that we determined from our table of values. Now, because of the size of some of these y-coordinates, 1/16 and 1/4 and 1 being so close to one another, and we're going by 5s, it's impossible to plot all those y-coordinates the same. But what I would like is for you to make sure that as you're going from left to right, that each of these little points is a little bit higher than the previous one because, well, as we increase the x value, the y value is increasing slightly at first. Then it starts making big jumps. We would go from 4 to 16 to 64 and so forth. Anyway, now we're going to go ahead and connect the points, and you're going to see what shape the graph of an exponential function looks like. And here is that shape. And one thing I want you to notice is that I didn't touch the x-axis with that graph. And why do you think that is? Well, didn't we already talk about how you can't have a negative y value for this since the base of our exponential term is positive? So what that means here is that you essentially have a horizontal asymptote, and not even essentially, you have a horizontal asymptote at the x-axis every time you're graphing a basic exponential function. And by basic I mean there's no translations involved. It's just some number to the x power. Alright, well, let's talk about some of these qualities in addition to that asymptote that you need to be familiar with. Yeah, I'd like you to know that the x-axis is the horizontal asymptote as I stated. I'd also like you to know that if you raise a number to the 0 power, you always get 1. And the reason why I say that is then the y-intercept always ends up being 0, 1. Just simply because when you raise any number to 0 power, you get 1. Alright, that's the graph of an exponential function, and in particular, that's an exponential growth function. Now I'm going to label that, and I think it'll make sense why it's an exponential growth function. Okay, y equals 4 to the x is the growth function, and it's growing. It's a growth function because as the value of x is increasing, the value of y is increasing as well. Plain and simple. Alright, next we're going to look at another function that's going to have exponential function that's going to happen to be an exponential decay function. And I think you'll notice as soon as you look at the equation that we're about to graph what the major difference is that will make this an exponential decay function rather than growth. And of course that difference is that the exponent here is a negative exponent. That's negative x. Alright, that's going to make this decay. Well, let's go ahead and plug in some x values, the same x values that we did in the previous example, in order to find out what the graph of y equals 10 to the negative x would look like. Alright, when we plug in 2, we're actually going to be plugging in 10 to the negative second power, which is going to be 1 over 10 squared, or 1 over 100. Then we're going to get 10 to the negative first power, 1/10. Then 10 to the 0 power, which is equal to 1. Alright, these are both supposed to be negatives down here. If I plug in 10 to the opposite of the negative first power, that's of course just going to be 10 to the first power, or 10. And then 10 to the opposite of the negative second power, it's going to be 10 to the second power, or 100. Alright, so all we need to do is go and plot those points, and we'll have our exponential graph. Now I hope you can see, as with the last one, when it came to trying to graph 1/100th versus 1/10th versus 1, that was pretty tough, so I just tried to make it so that each point was a little bit closer to the x-axis than the previous one. That's impossible to do absolutely correctly by hand. And let's go ahead and connect those points, and this is the graph of y equals 10 to the negative x power. Now just like before, you're going to notice that we didn't end up with any negative values because it was impossible. We had a positive base, 10, and it was impossible for any power of 10 to give you a negative value. In fact, it's impossible for any power of 10 to give you 0 as well. So this graph never touches the x-axis, and it's a horizontal asymptote. And also, we still had the point 0, 1 as our x-intercept. Happens every time until you start introducing translations or reflections or dilations or those types of things, which we're actually going to do in the next video. Okay, there you go. Pretty simple, right? And I already told you that this was decay because of that negative exponent right there. But another way of realizing that this function is decay, exponential decay, is because as the value of x is increasing, the value of y is decreasing, right? As we go further right, the graph goes further down. Exponential decay. Alright, got one more graph that I want us to make here, and it's going to involve a very special number that you need to become very familiar with. And that number is the number e. Now we'll talk a lot more about the number e in class, alright? But basically, let's say it can be referred to as the natural growth constant, just like pi is a constant value, 3.141596. You know that pi is an irrational number, but it stays the same, right? Well, e is another irrational number, another famous irrational constant. All right, so you need to learn how to graph exponential functions involving the number e and how to solve problems with the number e in general. Well, I'll help you with that, but let's go ahead and basically make our table the same way that we did with the other two functions. And I hope you can already tell that this is going to be exponential growth because that's not a negative x, it's just a regular old x there that we're trying to graph. Now I'm going to start off in the middle of this table of values. You know that e to the 0 power, just like any number to the 0 power, is going to have to be equal to 1. Alright? And you can say that e to the first power is e, which if you use your calculator, you're going to see that that means it's about 2.72. Alright, and then e to the second power, again, just use your calculator. You'll find an e to the x button on your calculator that you can use to figure out this value. And that's approximately 7.39. Alright, now e to the negative first power would be the same thing as 1 over e to the first power. And then e to the negative second power would be the same as 1 over e squared. So just use your calculator, figure out what those two are real quick. And you'll get these values, 0.368 and 0.135. Now, just as with before, the x-axis is a horizontal asymptote. The graph will never get there. It will never go below it either. And the 0, 1 is the y-intercept. All right, plot the points, make the graph. I'll be drawing it as well, and you can check yours against mine. Alright, there are the points plotted as close as I could get them to show you that it's increasing over time, as any exponential function graph will do. Exponential growth function, I mean. And let me connect them. Alright, there's a graph of y equals e to the x power. Very important graph for you to be familiar with. Especially when we get into calculus, you're going to have to use this function e to the x quite a lot. Alright, now there's no problems from the book that asks you to graph these simple functions the way that I did right here, but we're going to get into translations, reflections, and that kind of stuff, and then you'll have some problems to graph. So check out the next video, then you'll be ready for section 4.3.